So, good morning, everybody. So, my name is Knut Andreas Lie. I'm chair of the conference. I'm very happy to welcome you all to Stanford. We will have 4 days of science and networking here, which I think will be a great fun for all of us. Altogether, so far we have 425 pre-registered full-day participants. We have 6 plenary talks, and the plenary talks will have a meet the speaker later in the day. This is a new thing that we'll do here. There are 73 parallel sessions. Each will consist of 6 talks of 20 minutes. And these consist of 63 mini symposia and 10 sessions with contributed talks. And for those of you who can do math, you'll probably figure out that there are more speakers than there are registered participants for the conference. So I guess there will be even more people later on. We will be having 2 poster sessions. They are outside here. Altogether, there will be 50 posters. And we will award prizes. So if you see somebody walking around with a sheet of paper and noting down something on your poster, that will be those who will give you prizes later on. So you need to treat them very nicely. And if you see me, I will need to be treated especially nicely, of course, because I have nothing to do with this. We will also have the prizes for the career prize and the junior scientist prize later, and then we'll have the business meeting. And some of you have already been here because yesterday we had an early start where almost 200 participants were part in 14 different courses that took place here. So I'll do just a very brief history of this conference. Some of you may have been to this conference series many times previously. This is called SIAM Geosciences 15 because it's 2015, but in fact it's also the 15th conference that has been conducted in this series. And here you can see the number of participants that have been through all the years. So, so far, 1985 was a high year with over 500 participants. This year, as I said, we have 425, but we think that that is a modest number that will increase by approximately 50 or 100 more people. So we'll reach almost 500 people during the week. I would like to thank all those who have made this possible. First of all, I would like to thank my co-chairs, Sorin. Sorin, are you here somewhere? Yeah, Sorin is at the back. And the one that has actually done most of the work is Margot. She will come forward and then you should applaud her afterwards. And then I also have a list of committee members. You can read all the names here. And they all contributed to making what I think will be a great conference. Some practical information. There is a free Wi-Fi here. Most of you will probably have noticed this already. There is coffee, which I also think that most of you have noticed. Mathematicians seem to work by coffee. Please be sure to report all cancellations and substitute speakers to the registration desks. This is very important. And please also make sure that you are on time for your presentation and that you're early so that you can upload your presentation to the session chair's computer. Changes to the printed program are available on the web page, but, and also maybe on the mobile app. But please use the program at a glance to check room locations and so on, and not the big book of abstracts, which unfortunately is a bit outdated. And there will be plenty of signs that will tell you how to go around, and then people will have these nice t-shirts that Margot will now come and demonstrate for you. So Margot, please come up and...
Hi. So welcome to campus. It's an absolute pleasure to see all of you here, and especially a lot of old friends. It's just fantastic to have you on campus. The sun is just starting to break through. It's going to be a hot week this week. If you forgot your sunscreen or your hat, if you don't have that much hair anymore, we have some spare ones at the info session as well. Couple of things that I want to point out. In the morning when you come in, breakfast and coffees are always available here, so if you like bagels and muffins and scones and coffee, then you don't have to have breakfast in your hotel, you can come straight here. We have coffee throughout the conference. Lunch is also going to be outside. As you can see, there's tables, they have parasols, so we have some shade as well. Really important is to know how to get to Bechtel. There are 2 concurrent sessions in the Bechtel Conference Center, which is 3 minutes walk from here. There's Oxenberg Room and Bechtel Main. Those are listed in your program at a glance. If you're there, just take a few extra minutes to get to that mini symposium or contributed presentation session. You leave the conference room or the conference here, the main entrance of Arriaga, you turn right and you follow the signs. Okay, so there's a couple of big signs posted to lead you to Bechtel. Shouldn't really be a big problem. Really important to always use this to find room locations. Okay, so you all have this. If you don't have it, you need to get a copy. Do not look at the big book, because that has the wrong room location, okay? So always just use this one for room location. Can't tell you that often enough. And for those of you who haven't discovered it yet, at the back is a map of this conference center that shows you the location of the hall you're in right now. This is McCall Hall, and Fisher, which is on the other side of the building, okay? And it also tells you how to get to Bechtel. So here is this map. And then there's another really essential map, that's this one. If you don't have that one, you have to pick that up too. That shows the location of the reception tonight. So tonight from 7 or a little bit before 7 to 9, we have a reception with plenty to drink and some food as well. So those of you with not too big appetites, you're going to be fine. Nobody will be starving. There are no tickets for wine, which means you can drink as much as you like, but when the wine is gone, it's gone, okay? So that means you have to drink early. Music will be provided. There will be a small high school jazz combo with my son playing the drums. So no criticism on the band tonight. But again, it's a pleasure to have you here. If you have any questions during the conference, there is an information booth, which is next to registration. And you can ask any of the people in the white funny t-shirts. But the information booth is manned. 2 other quick things. If you have a hard time walking, we have golf carts to take you to various places. So if you need a lift to Bechtel, tell the info booth. They have the key to the golf cart. They will take you there. If there's anybody here who doesn't hear that well, we do have an ASL interpreter. So just let us know, and then we can have him help you in any of the sessions you're going to. Okay, so also then let the info booth know. That's all I have. Over to the session chair.
Okay, thank you very much, Margot. And if you're happy with the conference, you should tell Margot. And if you're not happy with the conference, you should tell me. So a last thing here, a message from SIAM. And not everybody who are present are members of SIAM. And of course, we encourage you to become a member. If nothing else, you will save $130 by being member next time you sign up for a SIAM conference. So with that, I wish you all a very nice conference, and I hope to talk with as many as possible of you during the week. Thank you very much.
All right, good morning, everyone. We have an exciting program in exploration geophysics at this SIAM GS conference this year. And to kick things off, we have Fons ten Krode, as a plenary speaker, he's no less than one of my favorite seismic imagers of all time. I'm really delighted to have him here. He started as a mathematician and theoretical physicist, joined industry, and continued his research activity as a mathematician. And not as a sideshow, but as an integral part of his activity in the company. Seismic imaging is intellectually interesting beyond your expectations for the students in the room. So Fons is really a great example of that. So he started his career with short postdoctoral stays at University of Illinois and University of Amsterdam, joined Shell in 1991 as a research geophysicist, and is now head of the Seismic R&D program at Shell. Please join me in welcoming Fons ten Krode.
So thank you, everybody can hear me? It looks like that. Thank you, Laurent, for the gentle introduction, and thanks to the organizer. Maybe this should be switched off, because thanks to the organizer for inviting me. It's really, I'm honored to be here. I have to say that I was pretty late actually suggesting the title of my talk, and I was so late that the initial program was already built, and when I saw it, my talk was scheduled for Wednesday or so, and there are at least 4 or 5 other FWI sessions, which is part of what I'm going to talk about, already before that. So I wrote to the organizer and said, well, maybe it would be an idea to move me a little bit up front, and much to their credit, they immediately did that. But now, of course, I'm faced with having to break the ice at this conference. I'll try to sort of whet your appetite for the FWI sessions during this conference. There are 3 today, and 2 more actually tomorrow and Wednesday. So here's the outline of the talk. Since this is a very general audience, I see a couple of my friends and experts in seismic imaging in the audience, so that's okay, but there are presumably many people that are less familiar with exploration seismology, so I'll start with a crash course on that. I will argue that the main problem is actually to estimate velocities, seismic velocities in the subsurface. So the second topic will then be to talk about what the industry has done, and industry and academia, of course, over the past 25 years. So that is the topic, classical velocity estimation. I'll try to make this a little bit tutorial, and I do that in particular because it may make my life easier when I talk about the last and most advanced topic. This is wave equation-based seismic velocity estimation. So what do we do? This is what we do. We go out to collect seismic data. This is an example of a marine seismic acquisition where a boat sails and it drags a cable, or actually a number of cables, and these cables have hydrophones, pressure sensors, every 6.25 or 3.125 meters or so. There's plenty of them. Cables can be very long, up to 12 kilometers nowadays. So the most modern marine seismic acquisitions have over 100,000 sensors being towed behind a seismic boat. Apart from these sensors, there's also a big gun, an air gun, which is really a pressure chamber. The air is being pumped in that chamber, and when it's released, an air bubble travels in the water. It hits the ocean floor, and it propagates as a seismic wave into the earth. And whenever that wave hits a discontinuity, because of a different geological layer, it gets partially reflected. And that reflection is what we measure in the hydrophones. Okay, I would like to start with a very simple analogy. This is the fisherman analogy. So these people want to know where the fish is. And they have an echo, right? So they send out a pulse, and they measure the time of flight when it comes back, divided by 2, and by the velocity multiplied by the velocity of water, which is give or take 1,500 meters per second, and then they know the depth of the shoal of fish. This is the simplest imaging problem that I can think of, and it's still very profound because there is a velocity, 1500 meters per second, and there is a scattering object, namely the shoal of fish. In our situation, the seismic exploration, the thing is that we don't know that velocity. Well, we know the velocity of water, but everything underneath is unknown. And that is the reason actually that we collect redundant data. So if this is a streamer with receivers R1, R2, and R3, then you see the ray path that go from a shot to a reflector and are then being measured. And as you can see, the seismic record, which is measured, is underneath. It just consists of a bunch of seismic traces, and in this situation, each trace has only a single blip. And for the receivers that are a little further away from the source, you'll see that the blip comes in a little later because the travel path was longer. And if you do a little bit of high school math, you'll see that this is what we call the move-out equation. It tells how the arrival time of these blips varies with the distance between source and receiver, which is also called offset in exploration geophysics. So if you have the t squared is t naught squared plus h squared over c squared, it tells you that if you measure this curve, I can, in principle, by looking at this curvature, find the velocity. And if I look at t naught and multiply that by c and divide by 2, I get the depth of the reflector. That's the general idea. Okay, I'll refine this concept significantly, but let's look at real seismic data. So this is what comes from a streamer, and this is a streamer that sailed in the North Sea. And yeah, the only difference with the picture that you just saw is that there are not 3 traces, but there are a couple of hundred that are placed tightly together. And I've now, what people do is that any positive oscillation is colored red, and any negative oscillation is colored blue, and then you get a picture like this, right? And you see this hyperbolic move out that was in the cartoon. Okay, now, so the boat just sails and sails and sails, and it shoots and shoots, so it collects tons of data, shot records we call them, and now this is now the central problem. How do I transfer these data into an image of the subsurface? Okay, obviously we need a model for wave propagation. And the simplest model in use is currently simply the acoustic constant density wave equation that you have over here. If we take the source signature W of x and t equal to a delta function in xs, the location of the source, times some sort of time series, a W of t, it's called a wavelet, then P had a pressure that will just be that wavelet convolved with a Green's function, the fundamental solution of the wave equation. And you see in the bottom a finite difference, a snapshot of a finite difference calculation of wave propagation. So you see what a wavefront does in a fairly complicated geological setting with a salt body that scatters the wavefront. Okay, in order to proceed, what is typically done is that the velocity function that is unknown is being split in a slowly varying smooth part, it's called C naught of x, and a quickly varying discontinuous part, delta C of x. And if you think back of the fisherman analogy, then C naught of x is of course 1500 meters per second, and the delta C of x are the fishes, right? So that is a scattering object. It enables you to linearize the acoustic wave equation, right, just by taking the formal derivative with respect to C naught. And that equation, the linearized wave equation, can be solved, of course, if you would know G naught. And that solution here is called the Born operator. So this Born operator takes reflectivity, which is really 2 times delta C over C naught cubed, and it makes a sandwich product with 2 Green's functions and transfers that into seismic data. we typically make more approximations, and these are to a large extent historical. Solving the wave equation by finite difference method was for a long time too expensive, so we typically resorted to asymptotic approximations where a Green's function is just a sum of traveling wavefronts. And such a wavefront can be described by an amplitude A and a travel time function tau, and these quantities can be calculated by ray tracing. What you see over here is actually a couple of rays and wavefronts which are calculated in the Marmouzy model. And I couldn't resist showing this model because it's this year 25 years ago that that model was introduced in the EAG in Copenhagen, so a bit of a celebration. It has sort of triggered so much research that can hardly be beaten. Okay, here are the fundamental facts about the Born operator in its high frequency approximation. It is a Fourier integral operator. Okay, and even more is true, that's spectacular work by Greg Balkin in the early 80s. If you take the product of that Born operator times its adjoint, you get a pseudo-differential operator. Pseudo-differential operators are, of course, a generalization of normal differential operators, and their basic property is that they don't move singularities. So if I have a velocity function which is discontinuous, then that discontinuity will not be moved by the pseudo-differential operator. So there's a simple corollary here. If I have data that is related to a reflectivity, which can be singular, by this Born operator, and then I apply the adjoint, then I get the singularities in my reflectivity back, because B naught star times B naught cannot move these singularities. Wow. So I have an imaging operator. To see how this works, I have a Green's function from source to reflector, and a Green's function from the reflector to the receiver. This is the Born operator. It's just a sandwich product, right? Now, the adjoint, what does it do? It turns back time by applying with the adjoints. And here you have the adjoint operator in its full glory. And this is now an imaging operator. This is an example of an image which is taken from seismic data in the northern part of the Netherlands. It is the result of just applying the adjoint. And you can see that the Netherlands, which is fairly flat, is not so flat at 3 kilometers depth. We have large salt mountains, for example, so this, for example, is a salt diaper that comes to surface. So this is a salt mountain which is 3 kilometers high, just like in the Alps. This is absolutely amazing. So, am I done? Of course not, because I've hidden the most important part. I need to find that velocity function. The Born operator and the adjoint of the Born operator depend on C naught. This was actually only the linear part of the problem. That's easy. The nonlinear part, that is what this talk is about. Okay, in order to explain how people have gone about this, let's look at that adjoint once more and let's do a dimensionality check. So my seismic data depend on sources, receivers, and time. And sources can vary over the surface of the Earth, so they have 2 coordinates, and receivers as well, also 2, and there's time. So data are 5-dimensional objects. And the images that we're looking at only depend on X, Y, and Z. So 3-dimensional objects. So the data is redundant, as I already remarked in one of the first slides. So how are we going to take advantage of that? I'm going to define offset as the difference between source and receiver vector. This is a vector in the horizontal plane, so it has 2 coordinates. And I'm going to define offset extended image gather. So it's just the adjoint, but I'm not summing up over all receivers. I just replace receiver by source coordinate plus this offset, as you can see. So now I have offset extended images that suddenly depend on 5 variables. And this operator that is defined over here maps functions of 5 variables to functions of 5 variables. That's very nice. Let's have a look at what such an offset extended image gather really looks like. This is what it looks like. So I have now fixed X and Y. I'm looking at the Z in the vertical direction and offset the redundant parameter in the horizontal direction. And as you can see, it's all the same. That's not surprising. This is just a redundancy. If you sum everything together, you get the full adjoint again. And this leads to an improvement in signal to noise, of course. The thing is that this data and the image are associated to each other by the fact that they both are associated to the same velocity. So data was created with C0 and image was also created with C0. So it's all correct. However, if you now start to vary the velocity, you see something strange happening. You see that this offset extended image gather, which was originally flat, starts to curve. Now that's nice, because it means that I have a control knob on velocity. I should just make sure that my image gathers are flat. And that is the basic principle of reflection tomography. Okay, let me see how this then works in practice. So this is if the velocity model were correct. The gather is flat. This is if the velocity model is a little too fast. So the gather is curved. And now measure the depth difference between these two. I'll get back to that. I can relate that depth difference to an image perturbation by a simple formula, which is due to Teagle, Schleicher, and Hubral. That's that first formula over there. And I can also, by making use of the definition of the offset extended Born operator, find out how the offset extended common image gather varies with velocity. And you get then, if you fill in the asymptotic representations for Green's functions, you get travel time differences that are related to velocity differences. And you can calculate these through Frichier ray tracing. Okay, if we put everything together, then what I get is a linear system of equations. So the delta z, so the change in the depth of the image as a function of offset, is related to the delta z, the velocity change in the overburden. That's the one I would like to know. So I just need to calculate the sensitivity kernel k, that's done through ray tracing, and then invert this large linear system, and I find an update for my velocity. Okay. Now, what I've wept under the carpet is that you can't really measure delta z because the depth of the reference reflector is unknown a priori. So in order to mitigate that, you just take the difference between two delta z's at different offsets. Then this unknown reference depth drops out, and what you have here is again a linear system that I can invert for, and it looks very similar to the differential semblance or linear differential semblance optimization, which was introduced by Bill Symes. Okay, this is how it works. This is a data set from the Northern Netherlands again. Those of you that know the Netherlands see the Waddeneilanden, the Dutch Isles. This is a big survey that we acquired there many, many years ago. You see a velocity model. There is a salt mountain again, a diaper. This is the sedimentary part of the velocity model. There's chalk over here, there's salt over here, etc., and typically we want to look somewhere underneath. You see these offset extended image gathers on the left-hand side in the model that we have over here. And if I flip to the next one, then you see that they are changing. In particular, if you focus on the right rectangle, you see that curved events are being flattened. That was the principle of reflection tomography. And you see also the velocity model on the right-hand side changing. Okay, I'm done. Well, unfortunately, the oil industry is moving to ever more complex settings. Here are a couple of examples. So I guess we've all heard about the Gulf of Mexico and Brazil, which are salt-dominated provinces. You see over here, these salt mountains over here, and we typically want to look underneath, of course. This is another example that's also typical in current exploration practice, fault shadows. There is a big fault in the subsurface, and on one end the image is good, on the other hand it's really poor. You have gas clouds that we see in the Far East typically, and then the most elusive of all, basalt, right? So how can we look under basalt? Extremely, extremely difficult. So what is the issue with these complex geologies? Why does it not work, what I just showed you? Well, first of all, there's an issue with the ray approximation. It's only valid if the medium varies smoothly. And here is an example of a geology. It's a synthetic model, it's a 6B model, where that is not the case. So there is salt in this model, that's this, and the salt is rugose, and you see that the bundle of rays that we shoot upwards, as soon as it emanates from the salt, the rays go in each and every direction. If I measure their arrival time, then you see that arrival time looks really rugged. I mean, that's not, this defines the adjoint operator, and that operator is summing over this arrival times, and that function is not smooth at all, so that's not good news. If I calculate a Green's function by finite differencing, you see that actually, it isn't so bad. It's complex, but it is not so erratic as the rays seem to suggest. So this is really a motivator for the fact that in these complex settings, I can't do ray-based theory. I need to go to a wave equation-based theory. There's also a fundamental aspect here. That's namely that the normal operator associated to the surface offset extended Born operator that I introduced can fail to be pseudodifferential. And that leads to artifacts in these subsurface offset extended images. This is actually showing me that we need to do something else. This surface offset extension isn't good enough. I need to come up with a different way of exploiting the redundancy in the seismic data. Okay, now I'm coming to the last topic of the talk. So I want to talk about the most modern methods to estimate seismic velocities. This is, I'm going to talk about two building blocks that are emerging at the moment. One is FWI, full waveform inversion, and the other is wave path tomography. So FWI actually is already quite old. It's a natural ID that stems from the early 80s. It's just saying, well, why don't we minimize the misfit between field data and synthetic data that satisfy the wave equation? And as it satisfies the wave equation, then depends on the velocity. So you optimize this while varying over the velocity. A very attractive ID, right? Because this is in principle, it can work with full wave equation based solutions, finite difference or finite elements or what have you. I'm going to explain that there is a fundamental problem with this approach. It's known in the community as the loop skipping problem or the non-convexity of the L2 misfit functional. So I started out by explaining this simple relation T squared equals T naught squared plus H squared over C squared. So I have here three reflectors that are sort of floating in a constant velocity medium C. That is the cartoon problem. And I'm now going to change the velocity. I'm going to slow it down. So what happens, everything comes in a little later, and also the curvature of these events is going to change. Right? So if I plot them all at the same time, this is what you see. You can already see the problem coming. They are out of phase. You need to sort of change the velocity so that the curves, the dashed curves coincide with the solid curves. How are you going to do that? Let's focus on the central trace, the zero offset trace. Here is a movie that my colleague Wim Mulder made that beautifully illustrates what the problem is. So there are 3 pulses, and the ones that are moving in are the ones for which you're changing the velocity. And in the bottom, you see the least squares misfit function. Right? So in places where everything is out of phase, it is completely zero. In other places where one loop coincides with another loop, you get a local minimum. And only in the middle, when everything coincides, it perfectly subtracts, and then you have the minimum of the misfit function, the L2 misfit. This is not an attractive function to optimize, obviously. It's highly non-convex, and any gradient-based method is going to fail. It's going to end up in a local minimum. If you think about the reason for this, it's really that seismic data is deficient in the low frequencies. We typically in field data see frequencies down to 5 Hertz maybe or so, maybe a little bit better nowadays. But it's very hard to generate low frequencies, and that if you think about your stereo at home, you will understand why. You need a big woofer actually to generate these frequencies. If you would have them, and then you could go to a very low frequency band, and the waves would be broader, and therefore the loop skipping problem might be less. But unfortunately, that's not the case. So we can mitigate this a little bit by working with a different part of the wave field. So apart from reflections, there's also something that we call diving waves. They are present if there is a velocity gradient in the subsurface. And refractions, they are present if there is a strong contrast in the subsurface. These can be observed in seismic data in the red rectangle. And the problem tends to be a little better posed. I'm showing you a field record here. This is from a land seismic data set from Oman. And on the left, you see model data in black, if you can see the black, on top of field data in color. On the right, so the model data were modeled in an initial estimate of the velocity model. On the right, you see the same, but now in the estimate of the velocity model that full waveform inversion has come up with. And as you can see, on the right-hand side, they are perfectly in phase, because I see only blue shimmering through, which means that the black of the model data is on top of the red. So FWI has changed the model so that the data become in phase. Precisely what it should do, of course. So what was the effect on the model? Well, here you see it. We started with a linear gradient, a function V of z. It's very far away from the truth. And in the bottom you see the model that FWI came up with. This is quite a spectacular result. This is the Maradi fault zone in Oman. It's one of the most extensive faults in the Middle East. It's very hard to image, and the full waveform inversion just worked fine here. I have another example, which is also one of the highlights of our work. This is from offshore Nigeria, where we're producing from a field, and the field has, it's an oil field, but there's a gas plume on top of it. And so this is the anticline that holds the hydrocarbons. And on the left-hand side, you see our best guess based on reflection travel time tomography, the method that I explained to you. On the right, we see the FWI result. And now suddenly, you see a quite different picture. You see that there is a slowing down of the velocity. The blue is really much, much slower, which is associated to the gas that comes out of the solution. And there is a speeding up, which is interpreted as a gas hydrate. So the gas hits the cold ocean water and freezes, actually. So also quite a spectacular result. And you see that the image itself also changes, which obviously has an effect on how you're going to produce a reservoir. Okay, so pros and cons of full waveform inversion. It can significantly improve velocity estimates if it works, because it is prone to loop skipping. And the other important con is these diving waves, they don't go extremely deep, or you could say they do go deep, but they end up in very far away from the shot that generated them. So you would need very long offsets in your seismic acquisition, which aren't always available, or everything's available, but at a price. Okay, that brings me to the last part of the talk. So we need to complement this full waveform inversion by something else. And that something else is a direct generalization of what I started out with, reflection travel time tomography. This I'll call wave path tomography, but it is just wave equation based reflection tomography. So recall that there is a fundamental problem with these surface offsets, namely that the normal operator associated to the surface offset extended Born operator is not pseudo-differential. So that leads to image artifacts. So we need a different concept. And I'm actually going here from surface offset to subsurface offset. Let me illustrate that. This is just a reflection, and you see the distance between XS and XR at surface is called surface offset, of course. But if I take the intersection at a deeper level, Z, then the distance between the rays is called subsurface offset. This concept is called survey sinking. I can multiply by the adjoint of a Green's function, and I do that again. And that means, as I've already explained, that you take away that travel time, so it's like you've brought your survey down to the level Z, that depth level, which is below the surface of the Earth. So the formula that's associated to that is as follows. You take your data, you hit them again with a sandwich, you make a sandwich product with the adjoint of Green's functions. You sum up over sources and receivers, and you get a data set as if it had been acquired by a source here and a receiver over there. That sort of opens up the idea, well, what if I go deeper and deeper and deeper, right? So what if I actually, this depends on time, what if I put the time equal to 0? Well, clearly then everything ought to focus in an image point. So what I've done here, I have created so-called subsurface offset gathers, and I've argued that if I backpropagate, so I make the sandwich product with Green's functions that live in the right velocity model, then everything ought to focus in the correct location, in h equals 0. This is what the subsurface offset looks like for a model with 4 reflectors. So you see here h along the horizontal axis, z along the vertical axis. The velocity model is apparently perfect because everything is focused in a point. However, if I now start to fiddle with the velocity, I make it either too high or too slow, you see that they're not focused at all. So I have again a control knob on velocity. I can sort of require that the velocity is such that all these subsurface offset gathers are perfectly focused. Okay, how do you formalize this? So I've defined an operator that comes up with these subsurface offset gathers. It is really the adjoint of a forward operator that was introduced by Chris Stolk, Martijn de Hoop, and Bill Symes almost 10 years ago. It's over here. And we call this the subsurface offset extended Born operator. Clearly, it is an extension of the normal Born operator in the sense that if you let it work on a subsurface offset gather that's perfectly focused, it's the product of an R0 of x times delta h. then it coincides with what the normal born operator would do on or not. It's also, again, a map of a function of 5 variables to a function of 5 variables to show that it is an extension. Here are the fundamental facts about this subsurface offset extended born operator. First of all, it is a Fourier integral operator of order 0, which is very nice. Secondly, if there are no horizontal rays in your system, then the normal operator associated to this B tilde is a pseudo-differential operator. So, unlike the case for the surface offset, there cannot be any artifacts anymore in subsurface offset extended image gatherers. And then thirdly, under idealized conditions, I can actually invert this thing. And this can help you to arrive at explicit imaging formulas which don't only get the singularities in the right location, but also reconstruct the whole thing up to smooth errors. Okay. So it seems that in this setup, velocity analysis is all about focusing subsurface offset gatherers, which is a little different from the classical setup, which was about flattening surface offset gatherers. In fact, there's a link between these two concepts. It goes through a radon transform on these subsurface offset gatherers. So I can make a slant stack. So this is a subsurface offset gather. You see it's somewhat focused, maybe not perfectly because of the imperfect acquisition that we had over here. And you sum up your data along this line, which makes an angle theta with the horizontal. Okay, that sum up is formally a radon transform over here. And then, of course, if that thing was a delta function, then everything becomes just perfectly horizontal, right? So focusing means horizontal in the radon transformed. Here's an example of angle gatherers in a synthetic model. So what we've done, we've created first these subsurface offset gatherers by making the sandwich product. And you see on the left-hand side, and then we've done the radon transform, the slant stack. So you see on the left-hand side, everything is perfectly flat. On the right-hand side, we've used a velocity model which was too fast, and now everything is curving. So I'm back to where we started. Wave equation-based reflection tomography is all about flattening subsurface angle gatherers, right? You need to flatten something. Okay, now how do you do it? This is complicated, and I won't even try to explain this slide. The only thing is that to calculate, so there is again a linear relation between a perturbed image and a velocity perturbation, and the sensitivity kernel is calculated not through Fisher ray tracing, but by solving the wave equation zillions of times. So I've seen the numbers, and they are staggering in a real job. And at this moment, you're really glad that you have an efficient wave equation solver. This is super expensive, but it can be done. So here are, in that 6B model, a couple of these sensitivity kernels. So you specify a location x, you specify an opening angle theta, that's what they depend on, and then you calculate these things. This is why we call this wave path tomography. They look a little bit like a pair of rays, of course, but the rays now are not infinitely thin anymore. They are spread. It's really energy that travels along a path. This is what's going to be used for updating. So anyway, so here we had a model, a starting model, everything is curving, and then you run your update, and after 4 iterations, everything is flat. So it works. This was actually that model, the initial model. This was the final model update, and this is the actual velocity. So you see what we achieve. It isn't perfect, of course. And you see the tomography is giving a really smooth rendition of the reality, but this is what it is. We've done this on a real data set as well. So this is an ocean bottom seismic data set from the Gulf of Mexico. That is where you put detectors on the ocean floor, and you sail over it with a boat, and the boat just fires and fires, and there are typically over 100,000 shots that are measured by each sensor on the ocean floor. So really, really huge receiver records. And now we can do these calculations. We have a starting model, we calculate the sensitivity kernel based also on the data, and this is what you see. So this is our first sensitivity kernel based on real data. Very much the appearance of a wave path, so the energy is spread a little bit along the rays that you can still distinguish. And in fact, yeah, here we go. These are the gathers in the initial model and the gathers in the final model. It's working. We have a wave equation-based generalization of classical velocity estimation. Okay, I have 2 more slides. So one is on the outlook. If you look at my examples, the velocity models that come out of the methods, you'll see that they're extremely smooth. Maybe not a surprise, because that is what tomography does. In fact, if you do a vertical time depth conversion based on the velocity that you have, and you measure the temporal frequency, you'll see that it rarely ever goes above 1 Hertz. That's the temporal frequency content in a velocity model. Somewhat disappointing, I guess, but that's what it is. It is good enough to flatten the gathers, so to explain the kinematics of wave propagation. Seismic data, on the other hand, typically starts from 3-4 Hertz or so. So in between there's a band gap, which has already been mentioned in John Claerbout's book from the 70s. So if we would want to invert for the higher spatial frequencies in the velocity function, which we really want, of course, then we need to find a way to cross this gap. We can do that maybe either in better acquisition or by adding constraints or by whatever smart method. Then the second question is how to deal with elastic effects. Because the Earth is really an elastic medium, so the acoustic approximation is really, really very crude. And if I'm going to work on the reflections, because the kinematics is now correct, then I'll have to explain elastic effects on their amplitudes. And then finally, this is all hideously expensive. So the question is, when are we going to be able to afford this on an industrial scale? Okay, I don't think I need to say much in terms of take-home message. They are fairly obvious. The last point is I would like to mention a lot more needs to be done, and that's why we're here. And I would like to sort of encourage everybody to go to the sessions. Thank you so much.
Time for 1 or 2 questions. Please use the microphones, not like me over there. Don't be shy. Use the microphones, please.
I don't need a microphone. There's a notion that there's an expert in structural geology at the Signature. You've left out the expert knowledge of the other folks that are necessary to understand these things. Cannot the error in much of what you get when you get your final result be resolved by asking the experts what their opinion is?
Absolutely. Yeah. So I'm totally biased. That's the first thing, of course. I'm a seismologist, and secondly, whenever we drill a well in extremely complicated environments, we involve each and everybody that can bring something to the party. So in particular, geological knowledge and sedimentology and all the things that you can think of.
Yeah, but is it your idea to process all the data and then bring the interpreter into the process, or to hand it off and say I'm done and that's the only answer I can get?
No, in fact, at the moment it is maybe a little bit like that. So so processors they work, but have to say that in the velocity model building phase of the processing project, typically there is close interaction with interpreters. Because oftentimes if you, so we need to, as I said, identify these reflectors and pick, for example, the delta Z's. But you need to know what to pick. And in complex situations, that can be extremely difficult. So you need to rely on an interpreter, somebody with geological knowledge to do this for you.
I'm a reservoir engineer, so my main interaction with seismology is through time-lapse seismic, where we have the problem that changes in the reservoir can be in pressure or in saturation. Quite often it's difficult to distinguish between the two. So any hope that full waveform analysis is going to give us better time-lapse images?
Well, there certainly is hope, but you would have to see it in the seismic wave field. So either a velocity or a density change or so, that is something, or maybe, and I haven't spoken about that at all, in the anisotropy, so which can be related to the geomechanics that is changing. So the answer is yes, but it is not so straightforward.